Hey guys, welcome to Cellstat. I'm Abdul Azeez. I'm currently as a team lead working for generative modeling. So today's topic is regarding super resolution using GANs. So yeah, so okay, fine. To start about GANs, I just wanted to have a quick knowledge of what is the how much you guys know about GANs and how many know about GANs and how much they know about GANs. That's all. So from that survey, I can get to know from where to start, where exactly to start. Can you guys tell me like how many of yours know about GAN, basic GANs, basic, and how does it work? What can it do, like that? Cool.
More than 50% don't know the basic intro to GAN.
Okay, yeah, that's totally right. So, and how many of us know about image processing or computer vision? How a computer understands images, basic CNNs like that, and that is required. So fine, let's do a intro about GANs. That's what is one part of the this one is slide is. So intro to GANs is first is yeah, let us cover. So GANs, if you abbreviate, there are three definitions, which is generative adversarial networks. So it has two models basically. What it does is it creates sample data or it generates images. Generally, what we do is normally in any computer vision or any problems we consider, either we do regression or a classification. We never do generation like that. So GANs are something, a new concept where you can generate something new, or say you can generate a sample data. So first part is this one, generative. Generative means learn a generative model. We are training a model such that it can generate a data. Adversarial, trained in adversarial settings means, adversarial means you can consider as a faking or mimicking. Yeah, that's the exact word, mimicking. So that's called adversarial. Networks is the neural networks what we are building on. So we'll be using neural networks for GANs. That's so why generative models is I'll actually run through bit fast. If you guys have stuck up somewhere, if you have any doubts, please stop me. Okay, because this is already done in the previous session, which is WGANs. So I'm good. Yeah, that's why. So yeah, so why generative models? We have only seen discriminative models where given an image X, predict a label Y, which is a classification problem, gender classification problem, and or it can say estimates a Py of X. Py of X means what is the probability of X being Y, or what is the probability of a picture being a dog, a picture being a cat, like that. A simple basic classification. Discriminative models have key limitation. One is can't model probability of X. What it means is, what is the probability of image being image? That sounds odd, but this is the meaning. P of X is what is the probability of X being X. That is the probability of seeing a certain image, whether the image is there or not, whether the image is correct or not, whether it is right or not, that is there. Thus can't sample P of X, can't generate new images. Because of this, why why GANs were majorly introduced is because of the see, there are so many attacks, which is adversarial attack. You guys are new it or not. One is that so we are training so many neural networks for classification algorithms, saying dog cat classifies and all, but we never know how the model learns to classify dog, exact meaning of how it classifies a dog. So we understand that based on the some hidden features, latent features, it understands as the dog. The problem is you can mimic the transform. If a person can mimic the model, understand the model, and understands its parameters, get to know what are the latent features, he can forge an image such that which can be classified as a dog. This is adversarial attack. So it's if a image there is an image of a, let us say, a giraffe, I can, if I do an adversarial attack on a giraffe image, I can make the model to classify as a dog. That is pure misclassification. Another thing is it can be in multiple. This attack was seen in this one, speed limit signs and all. Since Tesla, there are more self-driving cars happening. So the speed limit, if whether the actual speed limit is for the human eyes written is 100, but the classification will be 10 or maybe 120, 140. So this is actually, this will screw up the self-driving cars. If a car is tested in that signboard, instead of 100 it goes in 140. It can cause problems. There are multiple problems like this and all. For a human eye it will look like 100, but they will they will change the parameters or certain pixel location to different high values. If you zoom the image and see, you will get to know that there are some dark points inside the pixel. It is very minute. For a human eye we can't get to know at all. But when you're doing a CNN, we know that we do max pooling and everything. What is a max pooling? Max pooling is nothing but in an array you take the maximum point. So this dark point will be detected. So this dark pixels will be detected instead of that 100 thing. So this is how smart is adversarial attack. It is not that easy, but it is possible. So to overcome this and all, we started generating new images. I mean, the problem with this one image thing is we need more sample data. Actual meaning of more sample data is wrong. We don't need more sample data. We need more variety of data. If we have a more variety of data only, model will learn properly. So for variety of data, you need to generate new data. Since we don't have the historic data, we need to generate new data. That is why. Okay, next is generative models cope up with all of the above because it can model p of x. It can say what is the probability of image being image, actual image or not. That is the probability. Next is, and can generate new images. If my image is given, it can generate different images of myself, maybe in a side, how I will look inside, how I will look in 180 degrees, 70 degrees, all the different angles. Multiple varieties are there. So next is, what is the magic of GANs basically? So if a ground truth has been, let us say this is ground truth is provided. If a image is provided, instead of classifying it, it will try to recreate the same image. So the left part is ground truth, and adversarial image generated by a GAN is called adversarial image because it is a fake image. It's not a real image. Okay. So this is the ground truth and this is the adversarial image. You can see that there are it is generating to most accurate, you can consider. So that is there. And magic of GANs is this one. Which one is computer generated? You can't get to know. So today's topic is also related to that only. This is super resolution images. This is actual original image, and this is a super resolution image. So you can't find out which is actually the actual image, which is super resolution image. That much accurate, or you can't say accurate. That much GAN has a capability to do it. That is what. Next is, what is the magic of GANs? Like this and so if you want to generate an image and you want to give some parameters of saying, like, okay, just think GAN is an artist. So if you want him to paint a picture, he can paint any picture, but you want to direct him to paint this picture. So that is where you give cues or user edits. I'll say that okay, in the painting I want the ground to be green. So he'll keep that into mind and he'll print this one, he'll generate, or he will paint it basically. So bottom is green. Then after that I'm saying like there should be some gray mountain or something like that. Then automatically it'll generate gray mountain. Blue color line which gives blue shades. So these stuffs and all can be done. Next is moving over adversarial training. Not this. Let's go to this only first. Yeah. So this is the architecture of a GAN. I'll wait for a second. Yeah, fine. So this is the architecture of a GAN. If you notice, GANs are not a single model, it is dual model. There are two training happening simultaneously. So there are two models. One is the generator and a discriminator. A generator its task is it has to generate new image. or it has to generate an image which is which looks exactly like a real image. So generator is kind of like a thief, if you consider, and a discriminator is like a police officer. It has to detect whether it is a real image or a fake image. Okay, so there are two tasks happening, two stuffs happening. One is the discriminator. Discriminator task is all about it has to identify what is real image, what is a fake image, what is the difference between it, what is the entropy, basically what is the difference, and it has to know what are the minimal differences which are seen between a real image and fake image, and it has to identify, classify as a fake. So discriminators, it is trying to find the or catch the thief, or this one, find the fake image. That is the task of a discriminator. Whereas as a generator, its task is all about it has to fool the discriminator such that its image is classified as a real. Get the point? Understood? Any doubts in it? Okay. So if you see this GAN architecture, one is real world image. Real world images are the training data sets we will be using it. X is the sample. You're taking a sample out of it. What is it? From a bunch of 1,000 images, you're taking a 10 images, sending it to discriminator, and this one generator input. If you notice over here, for a basic GAN, I'm noting it down. For a basic GAN, this one input is a noise. Noise is like, okay, if you turn on a cable TV and you don't have a cable, what the image you see? Some noise. So that is the this one input for the generator. Sorry. Some, not like disturbance, it's some random numbers which is a noise, because we know that if we can give a null image also, saying that fully zero, but since we are from neural networks, we know that for weights, instead of initializing to zero, we initialize to random variable such that it this one reaches faster, or it trains faster. Similar stuff is happening in generator also. Instead of giving a white image or full black image, instead of giving zero initialization, you give a randomly initialized pixel values to generate a noise. So you are sending us a noise vector over there to the generator, and output of the generator is an image. It converts what is it? Gradient descent, this one a random number into some pixel value such that it looks like the image. Image is nothing but a set of pixels, right? That's how. So and the output of the generator is sent to the discriminator. Output this one real image is also sent to the discriminator. Discriminator takes two inputs, does this one matching, keeps both the side by side, and checks whether it both is real or which is fake. So there are multiple ways of discriminating. One is very basic, is pixel to pixel Euclidean distance and all, whether exact pixel values are present or not. So there are multiple other ways to do it and all. So this ways of discriminating varies in different variety of GANs. In which GAN you are choosing, that metric will change, discriminating metric. So the output of the discriminating
example of like say WGAN and this one.
Yeah.
What are the? Its architecture looks the same.
Actually. Yes, totally.
Okay, where does it differentiate?
Wasserstein loss function change. Nothing else is different. So Wasserstein GAN is a method of changing the loss function. So there is different varieties of GANs. Everything looks 90% is the architecture is the same. 90 to 95% is architecture is the same. The small change will be there. That small change will affect a lot. Will vary a lot. So in the last topic, it was a Wasserstein GAN. Only the parameter which changed was a loss function. Instead of a general min-max, this one loss function, you use a Wasserstein loss instead of okay. Yeah.
I want to have a duplicate. What is necessary of sending the noise blank? Is there any starts with that?
It starts with a random number. So generally, see, y equal to mx plus c. We are solving from m and c. what we do as a human, we start with m equal to 0, c equal to 0, start iteration 1, 2, 3, 4, 5, finally end up. Instead of starting with 0, I give m is equal to some 10, this one c is equal to some 30. However, and even for random initialization also, we know what is the boundary. The values can range between, let us say, m and c values for my linear equation. I know that it can range between some 0 to 10. I can give any random variable, random number between 0 to 10 such that it converges faster than going to 0. So that's how the random variable happens.
So related question will be, given a use case, how do I decide which GAN to use?
That is, you need to understand about the use case. You give any, give some use case, then I can say which. Yeah, yeah, sure.
For operating something, basically a medical operation, where like in this case you have a lot of high resolution photos, or you need high resolution photo of a very minimal part. The rest of it you can have ordinary. In that case,
so in that case, you are itself saying, right? You need resolution. You need high resolution. So you use SR-GANs, super resolution GANs. You want to view the image. That is SR-GANs.
Even if I do photorealistic style transfer,
I'll come to that also. You can't do better. That is previous. Okay. Functions? Not random values, random layers, multiple layers. You're saying Z, right? Z? Is that for zebra? Okay, Z for zebra. Correct. Yes, quotient.
So now from a generator standpoint, is there any function that's basically taking those set of values from a population
No,
and then converting that into a sample?
No. See, it's not like that. Okay, generally a classification, if you take a image convolution layer, you'll get latent vectors. Autoencoders, yeah, basically this is the decoder. Think in decoder. You get latent vectors upscale to an image. That not purely decoder. It's kind of like a decoder part because it has a, it takes a latent vector, that is a feature vector, upscales to an image. Opposite of an encoder. That's all. Yeah.
So there are different use cases for various. So in WGAN, it is only able to produce limited samples of data, and because there is a mode collapse, non-convergence problem, because we are using simpler convergence.
So the issue about the WGANs is it takes a long time to non-convergence. That is still there. Versatile distance, basically. Instead of using a Euclidean distance or something, you use a versatile distance to find the okay. Exactly. Versus
the loss is really there at the end. Like how does the generator learn?
What does the generator learn? It gives a feedback. Discriminator gives a feedback saying it is fake. No, okay, fine. So there is a dual loss. Okay, there is a dual loss which is called min-max loss. I'll explain that. So this one discriminator will no wait. Discriminator will minimize the loss. Generator will try to maximize the loss because it is the loss of the discriminator. Okay, so discriminator will try to, I want to improve myself, so I want to reduce my loss. But generator task is all about I want to fool the discriminator, so I'll try to maximize the loss. So there is a min-max loss which is happening in GAN. Yeah, I'll get to that. So
maximize the loss.
So it depends on the way you code the function.
You just add a negative one and it will change. So it is. No, it does both. Both tries the optimization. Both will do the optimization. Let's come to the training. Then you will understand on that. No, discriminator has to minimize its loss. There is two laws, G loss and a D loss. So it will try to reduce D loss and increase the generator loss. But generator will reduce its loss, G loss, and increase the D loss. So if you in the loss function, I'll show you. Yeah. So for training the discriminator, first is see any interval or any forward propagation. At one forward prop, only one can train. Ideally, you can't train both because you will not reach to the destination at all. Okay, because of this min-max problem also. One is trying to pull, another is trying to push. So at any one instant, only one model is allowed to train. So in the first instance, let us say I am training the discriminator. So generator is locked, or the weights are not allowed to change. Update. Okay. So in the discriminator, this one images has been given to the discriminator, and random variable generator again it has a random weights. It will generate some random noise. If you can see over here, this is a random noise. So random noise is given. Images, real world images is given. Discriminator finds the entropy of those. Finds okay, which is real, which is fake. It understands that what are the features required for this one to find whether an image is a real or a fake. That is what it understands, that it automatically gives the output as fake because of the first iteration. Discriminator will this one loss will be very minimal, correct, because it can easily identify the distance between the two images will be too much and it can easily identify. So then after the it will give fake and the loss has been calculated. So loss of the generator will increase, discriminator loss will reduce. The output, the loss is again fed back to the generator. In the second iteration, generator knows that okay, fine, discriminator is smart enough to identify. I have to tweak my parameters in such a way that I can generate more pure images. So in the second iteration, discriminator discriminator weights are, I'll go down. Yeah. So back prop error to the update the generator weights based on the loss function. The delta W is been calculated. Then again W gets updated. Then in the second iteration, this one discriminator weights are freezed. Then generator, after updating the weights, it generates a more better image and makes the discriminator to identify whether it is real or fake. This keeps on happening. So yeah, so in generator action, okay, nothing has been generated here. This is for MNIST data set, you know that 1, 2, 3, 4, 5, 6, and all. So generator generally, you know, it takes a very large epochs to generate actual images. So this I took a random output of some 100 images, 100 epochs. Yeah, this is 10 by 10, right? Yeah, could be something. This all is generator image output. So generator in action means like how it is varying. So if you notice over here, if you identify starting, it starts with the black and finally it starts getting the edges and all. Slowly it start understanding, okay, this is how the you need to set. Yeah, this is not good example, I agree. Okay, this is the this one GAN formulation basically. So there is a min-max loss, which is a function of V of function of this one variance of discriminator and generator. Okay, so it is the formulated as min-max game. The discriminator is trying to maximize its reward. Yeah, same. I said minimizes loss or maximum. Correct. Probability of what? Being fake or being real? Fake. Discriminator is a probability of finding the fake. He finds the thief. He doesn't care about the. So there are two ways. You can either say that I don't want to, I want to find the thief, or I don't want to catch a person who's not a thief. So false negative, false positive. You can increase anything. In which way you say? Which one? Generator loss, it will increase. There are two loss functions. There are two probabilities. So either you can take the likelihood of being positive or being negative. Two ways. So both the way it will work. If you just interchange the parameters over here, if it is yeah, in this, what is the other function? Yeah, I'll come to the fact. There is a min-max theory. This one only. This is a discriminator loss. The left side. Log of d of x is nothing but probability of discriminator being probability of being in this case it is positive only, real, and in this case probability of the generated image being fake. Both. There are two images, two inputs is being given. Discriminator input is 2. So the discriminator will make sure the generated image has to be fake, as close. So it will maximize the probability of this generated image being fake and minimize the probability of real image being fake. Two inputs. Correct.
So the way that does that is D of G of Z.
Yes.
Right? So your generated image is going through
G of Z is passed through the
1 minus D of G of Z indicates the true images, right?
1 minus
D of G of Z indicates the true because the D of G of Z is going to
1 minus fake is
D of Z is fake, right?
1 minus fake is real. Okay.
Fake is real.
Correct.
So D of G of Z is the probability of fake, and 1 minus D of G of Z is probability of
okay.
real. So probability of real is what you're trying to calculate.
Okay. Okay. The loss function, what you're seeing is not exactly used in the this one code because of the Nash equilibrium, which is written over here. This is the loss function which is derived, which will work, but you tweak in a bit. I'll explain. So because of the Nash equilibrium, yeah, this is agreed. Yeah, in this case, both is increasing the likelihood of being real. Real. X is real in this case. X is a real image. X is real image. G of Z is fake image. No, we need to compare it, right? Which is real, which is exactly. How do you need a reference, right? Without a reference, how will you this one compare? Two inputs.
The first task for a discriminator is the log of D of X.
Correct.
Second task is 1 minus D of G of Z. Meaning
1 minus. Correct.
The ground truth and the fake image.
So ground truth is not known, is it?
Ground truth is known.
That is what you're saying. Ground truth is already known. And discriminator already knows that it's real.
Correct.
Discriminator has not been clear on the ground truth.
That is the point. So the discriminator has not been trained on the ground truth. So
correct.
That is why we need that.
Correct.
Right?
Correct.
Because if it was already trained, then we don't. Yes. The right part is comparison.
Cool.
So discriminator is running two times. D of X and D of G of Z. But generator is running one time. So discriminator is distinguishing for real X as well as what G of Z got generated. So discriminator runs two times for every run of G Z.
Okay. Then after running a maximization algorithm, when you differentiate, you get the maximum at the thing, right? So the maximum or maximum reward is achieved when probability of true and probability of this one real data and the generator is equal, being real, both is real. So that is arrived when d of x is equal to 0.5. Huh? Nash equilibrium is because one is trying to pull on another is trying to push. So if you put in a gradient, it is not even gradient descent or ascent, it is both. One is trying to go up, one is trying to go down, so it will start switching.
That is one kind of factor. The generator is like, I'm sorry, the generator kind of thing is one kind of factor.
Make it real.
Determine if it is
Correct.
another kind of factor. So both these are contradictory.
Contradictory and keeps your loss function, loss curve keeps on switching. That's why Nash equilibrium happens because of that. So, and the worst part is we found out that if we use this loss function, it converges very slow. So what we do is we vary the loss function in just adding a negative sign because of the in case of a generator and discriminator. And that is in the code, you will get to know that. So yeah, so in the discriminator updates is this is how the discriminator loss function is d of x and normal. So sum of all the this one epochs, everything. For every iteration, the loss is calculated, and finally you are getting average loss. And if you see the generator outputs, we are not taking generator gets only one input, discriminator input does not get. So that's why it is 1 minus d of g of z, because one again here also you want to increase the likelihood of generated image being real. Correct? Cool. This is maximization. This is maximization. Your this is minimization. This is maximization. It is 1 minus dg of z. Mini.
Maximization of that equation and then minimization of min-max.
Yeah, it is min max, correct. Minimizing this loss and maximizing this loss.
So it should be the other way around. Don't the generator seek to minimize the job of the generator?
In one case, you're
Maximizing the maximizing the probability of being real. In contradictory, minimizing the loss of probability. Correct, correct.
That equation, the top equation is the only one equation. No, within one equation, there are two things which are happening.
We're talking about the objective. The top side.
So from
discrimination perspective, top one is maximum.
So it is one equation. From generator perspective, I am trying to minimize that. From discriminator perspective, I am trying to maximize that.
Cool.
Equation is complete.
Saying the same thing. The purpose of the generator is to minimize the probability of being considered.
Because the bottom line has to be generated, this is semantic. You can word it both ways.
It's not about semantics. We're talking about the mathematics.
Guys, calm down. Super. Still, loss function is not finalized, guys. Wait. Loss function is not finalized. You keep on. This will not work. It is proven not to work. Okay. So that is why you again know about vanishing gradients, right? So when we use this function, when we use this loss function, the vanishing gradient comes up to the picture. So instead of this function, we are doing an alteration such that you get this function. This and this is both same if you understand. Correct? Because it is 1 minus. Here 1 minus is removed, but negative sign has been added. So that's what I'm saying from the starting. Minimize this function for the generator instead of instead keep the discriminator as it is. Yeah. So for a discriminator, you use this function. You use this function for a discriminator, and for the generator you use the minus wala function. So in this case both will try to descend. Cool, understood? Yeah, this is run on the phases. Yeah, this is celebrity data set and sure.
So what you're trying to say is that you're not using gradient descent anywhere. You're using gradient descent for both cases because of this symbology, right? Minus expectation of log B.
Yeah, minus expectation of being fake is same as.
Gradient descent only for the entire combination and alternating.
Yes.
Now you're not going to use gradient descent and gradient descent. You're going to use only gradient descent because you change the definition of correct.
Correct.
So now the function is not really flipping, right?
It's not.
Yeah, it's not flipping. Now it's just going.
No, it'll. No. It'll flip because. Yeah. See. 1 minute. It'll flip because the function is not a single function. It is a multifunction. Function of a function. If g of z goes high, d goes high. If d goes high, g of z will try to push it down. It is still there is a contradiction is there. If you are using this function, will not have Nash equilibrium. You will reach the convergence faster. If you use this function, then the Nash equilibrium will become very burst. Both the case will have Nash equilibrium, but convergence is approved or seen to be reached faster in using this function in the generator. No. If you see the loss curve, it is not gradient descent. Yeah, fine. Okay, it is gradient ascent in both the cases. This is gradient descent. This will turn to gradient ascent.
So can you go down? So 1 minus d of only 1 minus d of g of z gets changed. Which means the second equation completely flips. Which means you're only using coordinate gradient descent. You're not using gradient descent. You're only using gradient descent.
I can say that, but as per the curve, I can't say it is a gradient descent or ascent because the curve keeps on switching. If you plot the loss curves of discriminator and generator among the epochs, you will get. Okay, I'll show in the code. Yeah, fine. But as per the practical, I'm saying practically it is not the output of the generator and discriminator is not follows the same curve. If the generator goes down, discriminator goes up. It is, I don't know, convergence. To approve the convergence, I guess. Okay, this is the output of the this one, phases and cipher data set. This is the output. Okay, this all is fine. Intro to GAN is done, right? This all is output, just the output of different data sets. It's trying to using the basic GAN, how it is getting output and all. I mean, these are not the best GANs, these are basic GANs outputs. That's what is shown over here. Cool, you guys understood about GANs, right? Introduction to GAN. Any question ask now.
So I think this stuff you can even let's proceed.
Practically, yeah, I can explain practically, but it will take a long time for one epoch to finish. Fine, yeah, fine. This all is fine. So there are different GANs are there, which is DC GANs, everything. So DC GAN is nothing but if you use deep convolution, multiple layers, it becomes DC GAN. That's it. Instead of directly convoluting from upscaling from 1x to 16x, you do 1x to 2x to 4x to 16x like that. You're splitting the convolution layers. That time it will become DC GANs. This is seen to be giving good. So DC GANs are used for phases, to say for phases. Yeah. Yeah, multi-displays.
Do you propagate to the randomly generated vectors? Do you generate with that layer or only with the? Can you go to the?
Come again? What did you say?
Yeah.
This one you're saying?
No, no, the
Architecture.
architecture.
This one you're saying?
Yeah, in this, do you learn the parameters or you propagate one step back and one?
No. We can vary the input. Na?
Input place, you started out with the
Random variable. It is always random.
So suppose if you train it for very specific data, then you can even learn the distribution of the
That's what. This is a basic GAN. Basic GAN is always input is random. Some mesh. You don't need to give the input also sometimes if you tune it properly, but output will not be the same.
So you're saying that the generator is learning all the transformations from bad to noise.
That is the specialty of GANs. That's how it can do it. It can generate from nothing to something. That's a good word.
Can I learn a distribution like this?
Yeah, that.
When I start from scratch, the next time I will directly pick.
Correct. So if you see in the SR-GANs, we are not providing random noise. We are providing a lower resolution. This one image. So it is an image. Input is an image. I get the point. So in that case, you are sending a image instead of sending some random noise. So low resolution image input has been given, and it is a high resolution image. You are getting it as the output. Style transfer, you again send as an image only. You send the image, then you send the style also. Then it adds merges both, and it generates in a way such that the style is being imposed to the image like that. Okay, this all is fine. Okay, this is all about what are the challenges basically, and we've seen is one is non-convergence. One it is very hard. It is there is no one hard rule to find what is the reason of how to overcome non-convergence, because all the GANs will suffer from non-convergence. Generally, it takes very long time, and specifying the parameters or hyperparameters for each problem is different. And if you're training a GAN, there is no hardcore rule saying that like you specify this parameters, it will converge. That is not found at all in convergence. Non-convergence, you can minimize it, you can't totally overcome it or prevent it. Mode collapse, okay, I'll explain about mode collapse. Yeah, proposed solution is another is, if you notice over here, we are not giving any labels or not, everything. It is basic answer is more of like unsupervised learning. We are not providing saying that whether it is a cat, whether it is a dog, nothing. There is no y vector at all present over here. So, so one of the solution which is seen over here is supervision with labels. By providing saying that the image which is coming is a cat. So you gonna differentiate whether it is a cat and a cat. Real cat and a fake cat. No, see, okay, fine. After training the GANs, you want to generate a cat. If you use a basic GAN, if you have a training data set of cat and dogs, it will generate something which looks like a cat and a dog. You get the point. It'll understand both. It'll understand cat also. It'll understand dog also, but it will not know the difference between the cat and the dog. So it will generate both, and you can't specify a GAN saying that you have to generate only cat. So that's why the supervision happens over there. So if you provide a new input saying that I want to generate cat, then it will generate only cat. No, you have other options for. You have other option for auto labeling. You can do this one unsupervised clustering also. In SenseCard we did, right? So SenseCard we used use multiple very basic Euclidean distance also you can use to cluster. Then after that auto labeling. Labels at all. So how clusters happen, right? So it clusters happen based on the.
So that was one important thing.
Maybe it can be used. I don't know about that, but so far nobody has used.
No, approach for supervised and unsupervised data labeling. If it is supervised labeling, then do it. It can train that we generate label. Image capture, right? So for image capture,
You need training data for image capture.
I was thinking maybe somewhere in GAN there's a possibility.
So this one labeling unlabeled data is you can do it by similarity scores and all. There are multiple metrics for similarity scores. No, you cluster after that.
that's clustering.
After clustering,
Clustering makes it
Ha. By us manually given. You can give cluster 1, cluster 2, cluster 3.
So then there are ways of auto labeling, and there is something.
I don't know how do you train a computer to understand an image and say with
that's why there are syntax trees. So it has a semantic model, which is
you're saying about the knowledge graph?
it is how
Knowledge graph. Correct.
except it's not a it's a label which is very common. That's a CBR.
Yeah. Even that also. So, but that doesn't give labels, I believe.
Instead of using the last component, remove it. Store the embedding.
Correct.
If you feed in another image, if it's somewhat similar.
It will deconvolute to that latent. Again, that is a similarity score metric. So, it latent vector, even super resolution also use that.
Image to sequence. Image to sequence is like computation. You will take a CNN into another. Exactly. It is
Okay. Cool. Next is another solution is mini batch GANs. Instead of sending one image, label is output. Target Y label. Cat, dog, and
Okay, you're in the input to the discriminator, those set of images you're giving them.
input to the discriminator. Yeah.
Not the generator input, but the original image. And
No,
you're giving them those. Is that
actually it is in the both. I have not tried it. I have not tried it. GAN is a semi-supervised, I can say. Yeah.
But the Y label is not obvious, right? The Y label.
Cool. Fine. So, and next is mini batch GANs. Instead of sending one image and check whether it is real or fake, you send a batch, mini batch of 10 images like that, and all. That is one of the solution and all. So, info GAN is what? I don't know. It is type of a GAN where the architecture changes. I mean, what is inside generator? What is inside discriminator? Architecture of the convolution layers changes. That's it. Overall architecture will not change. Only the generator and the discriminator will change, or maybe the loss function will change. Nothing else is there. Okay, advantage of GANs is okay. These are the other generator models he was speaking about. Autoencoder, variational autoencoders, deep belief network, and Boltzmann machine. That is very old. Okay. Okay, this is all cool. Okay, two problems I'll discuss. One is the non-convergence. You got to know about this. Probability of distribution is implicit, not straightforward to compute P of x. So the GANs were introduced to find what is the probability of x being x. That is what is the thing. And okay, thus vanilla GANs are only good for sampling or generation. Very basic. You have 10 images. You have to generate some 20 images. So that time you use a vanilla GANs and generate, and it is proven it is not that good and all. When vanilla GANs are fully connected, normal neural network, fully connected network. That's it. No CNNs, nothing over there. So and training is hard. Fully connected, no CNNs. no CNs.
And sorry, related question. Residual networks.
Yeah.
Right. In terms of use cases, how would they compare with them?
We'll use residual networks in SR-GANs. We'll come there. We have to use those. Yeah. One is non-convergence. This is, you can see here. Deep learning one is minimizing. So because of this, instead of so other deep learning models has only one player or one loss function, and it is trying to minimize. So it is fine. Either it will be a gradient ascent or gradient descent. But in this case, there are two players, and one is trying to minimize and is trying to maximize. And not both are not independent. Both are dependent. When one goes down, another comes up. One another goes down, another comes up, like that. So because of this, problem comes and all. So we may not converge to the Nash equilibrium at all. That's what is seen over here. Okay, great example over here.
In a typical multi-object problem, when something is coming up and something is going down, you basically reformulate the objective function.
You vary the function.
Okay, something is going up, something is coming up, your objective is sitting.
That is the Nash equilibrium point.
Exactly. That's how it is. Right? When any multi-objective function, let's say you are minimizing cost and maximizing profit. It's always plus and minus, right? And then multi-objective function is basically converted to a single object function. Okay, it becomes a single objective function, and then you are trying to minimize.
You find an equation at the Nash equilibrium point, and I mean at the convergence point.
So the entire function becomes a single objective function. You can
Multitask loss also. Multitask loss.
So the multi-objective is now converted to a single objective function. Why can't we do the same thing here? Is my question. So we are talking about.
I don't know about the math. What you're talking about? I'm not understanding. I mean, see, it bounces off. Both bounces off at, but it still converges. That's what I'm saying. How do I say? How do I say? See, generator and discriminator both keeps on bouncing, but in the if let us say if a generator bounces at like 10 steps and discriminator bounces at 10 steps at first iteration, second iteration is not like it will jump at 10 and both 10, so it will reduce to 9. Second iteration will be it will jump 9 steps. How will I? 1 minute, I'll draw the curve and give you. Okay, I'm using the vacuum for the first time. Let's see how it comes. I'll just some page. Yeah, this is easy. Better draw in this. Cool. So if you consider over here G and D both, if let us say this is going high and discriminator is going down. What about? Okay, you understood, right? This is how the so if you notice over here, as per the epochs, it converges, but it doesn't converge quickly. It keeps on oscillating. It has to. I mean, this is not like fully, so it might be parallel somewhere. Okay, fine. I will just interchange G and D. At the starting, discriminate. No, this. No, D will start at. It is maximizer or minimizer?
No, G will start at. G will start at.
G will start, I guess. This is correct.
Yeah, G should be high.
Okay. No, no. At the beginning, at the first iteration, generated image will be a noise. A discriminator will comparison is high. So discriminator will not have a very what to say will be easier to find out it is fake. Yeah, discriminator low loss. That is why it starts with 0. Generator will have a very high loss. Correct. Okay. Cool. Okay. Just see this non-convergence basically. One of the example is the function is xy. If you compare this one, function has to be xy. In the first state, x is greater than 0, y is greater than 0. Function is also greater than 0. Correct. And see, increase the y increases, x decreases in the first state. So in the second state, just because the x decreases, even the y also decreases. So y decreases and x decreases. Then again, well, this one x is made to increase. So x increases, decreases y, and again you're getting increase in y. So from first state to fifth state, if you notice, both are equal. So this is what is the non-convergence problem happens.
So what you're trying to say?
I'm saying that one is trying to pull and another is trying to push, and just think there is a pen. I'm pulling this and you're pushing this. Both are pulling. Both are pulling. The state of this pen will be here only. It will not move.
Like a rope.
Rope. If you consider rope, this one is generator, discriminator and generator are in the both the side, and both are pulling the rope. The midpoint doesn't vary at all. It keeps on.
What is the midpoint?
D is equal to half 0.5, right? It has to be in mid. Discriminator should learn sufficiently enough such that it can discriminate the both. Generator should again learn sufficiently enough to generate really good image. So finally they'll come to a handshake, discriminator and generator. Okay, fine, I'm tired of fighting, you win.
No, actually that discriminator loses.
Yeah, finally
No,
discriminator loses.
By iterating for a very long time.
Very long time. So discriminator finally comes to a state, some saying that like, okay, fine, I can't learn more than this. There is no entropy present at all. So that time it loses. So that is what is. So non-convergence is over here also. If you consider this one xy and plot the curve, you'll get a circle. So wherever you start, you reach back to the circle. In a circle. That's what. Okay. Next is mode collapse. Mode collapse happens. Which one? This one. Yeah, this is better. Fine, guys. Just see here. Yeah. So this is the target. Round of dots you want to generate, but this one generator understands how to generate dots, and it gets overfitted over the dots. It generates only dots. It doesn't this one. So if you see the output, it understands dots, and but it doesn't understands the it have pattern of dots, and it generates only dots. Oh yeah. Or okay.
So I guess no question. This will not be the right question mark below. Because they're trying to.
There is no question mark at all.
No one has a doubt in caps. That's shocking. Or they slept or what? I don't know. Ah, yeah. So this one you can see is so one of the solution is okay, the supervision without, since it is unsupervised data. I was speaking about cat and dog. You have a training image of cat and dog, and you want to generate cats and dogs separate. What it happens is either it learns cat more or dog more, and it starts generating only cats or only dogs. That's how the mode collapse happens. It cannot be data imbalance. It is not able to differentiate between cat and a dog. If a two image has been provided, first image is cat, second image is dog, it is not able to learn the difference between a cat and dog, so it understands both the images same. Both the images belongs to the same label, and the mode collapse happens. Because you're not see at the instant you're not, since it is unsupervised, first of all you're not providing the labels. It thinks that ideally, okay fine, whatever the image you are sending is same label. No, that is ideal condition. No, probability of cat will be 1, probability of dog will be 0. That is mode collapse. Not discriminate, difference of the real world image, not fake or something. There is no classification.
So this is the case where the network does not learn.
Variety.
Network does not learn
Different classes.
It learns only one class.
It gets overfitted to one single class. Overfitted to. Agree, totally. Yeah, some solution is that mini batch GAN size set and supervision with labels. And yeah, recent attempts is the unroll GANs and WGANs. By using WGANs, you can reduce the mode collapse more, because this one it uses a earth movers distance, and it can the distance can identify more difference between intra-class also. I'll not take that here. Mini batches, that's what. Instead of sending one image to the discriminator, you send a batch of image to them. That's it. That 128 batch is different. Mini batches, very small. Instead of sending one, it is not sequential. It's parallel plus sequential. 10 image in parallel. 10 image parallelly 128 image. This is a batch. 128 is a batch. Mini batch is 10 images.
128 is a population.
Batch. We specify batch in the parameters, right? So that batch is different. That is like if okay fine, total data set size is 2000. Instead of sending whole 2000 to pushing into the training, batch wise 128. But 128 goes in sequential manner to the CNNs. We are not sending instead of sending in a sequential 1 by 1, you are sending 10 by 10 or something. Exactly. Weight updation happens after 10 images. Mini batch training, that's what I was saying. Yeah. That varies. That varies of what you want. If you want to get a mix of cat and dog, then you said in that case. Class information. Okay. No, if you want to mix up image, if let us say there are certain images you want to generate, okay, male and female both. So let's say male with some female hair. Exactly. If you want to mix up, what is your problem? What is your requirement? Based on that, you define. If you are training in that way, it will be hybrid animal, cat and a dog. Yeah, there are multiple other cases also, right? Yeah. So if you consider this one also, yeah. Your huskies and all. Huskies are like a hybrid of wolf and dog. Mode collapse happens very much in that case. I had it in the WGAN poster. If you see a wolf and a husky and a dog, it can't differentiate this husky as a wolf or husky as a dog. It can't differentiate at all, because by seeing also, you know that like husky doesn't look like a dog. Yeah. Yeah, this all is. Oh, okay, fine. Let's go there. How do I compare? Yeah. What to do? Main topic, I can just switch. That is not a problem. Cool. Let's start with the main topic, which is this an introduction to SR-GANs. SR-GAN stands for Super Resolution Generator Adversarial Network. Okay. Huh? It's not HD. It is not a high resolution image. It is called super resolution image. You guys know, but what is the difference between a high resolution image and super resolution image? No, DPI will be more in a super resolution image. DPI density per inch. Intensity. If you zoom and see, you will get more clarity. In high resolution image, images would look high resolution, but if you zoom, you will not get the information. You will not get the character.
So there is something like
that is what they say. Can't say ultra resolution, it is called super resolution. However you term it as, that's fine. So generally, that's what they say, right? It doesn't matter if your camera has 48 megapixel or this one 54 megapixel. Still, it can't beat the 12 megapixel DSLR. Why? DSLR gives more DPI. That is why. So that is more super resolution as compared to high resolution. So your phone photos, if it is 48 MP, you can take that photo, put it on a poster. Image will look good, but if you go close and see, you will not get the clarity. That is there. So that is. We are trying to get the information from that. So one is this. Let's. Yeah. Clarity. Yes. 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 Totally. Exactly. That is also playing. You are upscaling plus you're keeping the this one clarity of the image. Cool. Okay, fine. And disclaimer is, you will find a lot of Chinese and Japanese words over here because none of the Indians have done it. Purely this research, everything is done by more of Japanese. Even it is going on now also. Something non-Indian, I don't know. Okay, so discriminator generator and all, you know about it. Concept of GAN is, these are the different GANs. Vanilla GANs, if you notice over here, I was speaking about, it is a fully connected network. And DC GANs is a deep convolution network. You will have convolution layers, multiple layers in that. Info GAN is you provide the, what is it? You provide this one, I guess, labels. Info GAN is, you provide labels, I believe. Label information. I don't know, something I need to learn on. And LS-GAN, I don't know about that. I just took it. Cool. This is directly from paper, don't you? Yeah. Introduction is one. There are multiple tasks of application of GANs. One is the super resolution, what we'll be talking about. So the left side is this low resolution image. After doing a bicubic interpolation, you will get that. So if you, there are very basic ways of interpolating a small low resolution image into a high resolution image to get it. So after doing that, left side is that using GANs you will get the super resolution image. In painting is you have an image of your grandfather or something, and one part of the image is gone. You want to patch that. Could be. Yeah, if you want to patch it, what is this? Guys, don't sleep. Yeah. Good morning. Yeah, so this is you take out one patch of the image and you try to fill it back. So that is what is the in painting thing is. Style transfer is, he was talking about style transfer. So if you want to apply the style of grass on some game, that is how. So this is the left side is the green gas, the right side is a dried gas. This is style transfer. Blah blah.
One question. So if the eyes is, let's say, not visible, right, for some distorted image, how that eyes will be formed?
It is more on like you train the GANs full of faces, and GAN knows how a face will look and how eyes will look, nose will look, everything, and it will automatic. It on its own it will draw. You can think.
But it will not be the same.
No. See, generated image are not real images. Yeah. Generated images are called adversarial image. It will look similar to a real image, but not the real image. It won't know your grandfather. Yeah. Image credit is ISL. Everywhere it is.
No, but let's say if I have multiple other images of the same person and I train with them, probably it will.
See, you only say it's like if you consider your your age, your gender, and everything, your face looks, everything. Your eyes will not look so different as compared to.
Yeah.
Agree or not?
Definitely, yes. It doesn't change.
Difference between two eyes will be very less. No, don't go very minimal differences and all. If you see from a longer perspective, or okay, fine.
No, I can understand.
Ah. It will look like a real image, but not a real image. That's all. That's it. So SR-GAN is this is the SR-GAN, and the concept is from some distorted image or a low resolution image. The left part is the ground truth, right part is the generated image at the first epoch. If you consider, it will say that it is wrong. Then after that, it will try to over the epochs, it will try to generate a image which looks pretty much new, similar to the actual high resolution image. That's what it is. Yeah, I'm going to. Okay, fine. So it is similar to whatever the loss function you saw it over here. You're asking something? Okay, fine, cool. Yeah, same. The loss function is the real, and this one latent code is the ILR. So ILR means instead of sending some random noise, you are sending a low resolution image. That is what low resolution, high resolution image, real data. Cool. So generator part is it is a deep convolution network. I don't know whether you guys understand this pattern. You know about this patterns or not? Okay, fine. K means kernel, N means the filter size, S means the stride. This is yeah. This is Chinese terminology. Instead of giving some this one giving all the parameters, they give a codes for this so that they can use it and all. Okay, so first convolution is this one 9 kernel size, 64 convolution, and stride as 1 and all like that. So these are the residual blocks you were talking about. Yeah. So one skip using the skip connection also. Skip connection. Idea about it? Okay. Skip connection is nothing but it's kind of like resonate. Yeah, this uses resonate only. What is not? This is very deep architecture. I mean, it is shown. These small boxes are shown like this, but it is very deep. I don't know. I'll see the maybe 128 layers or something. Not 128 layers. 128 blocks. It is very deep. This one is very deep because see now we are performing 4x zoom. 4x zoom. 4x resolution is like your this one convoluting 1 pixel into 4 pixel. 64 by 64 into 256 into 256. So it is like if a value is 1, you are generating a matrix which is having the same information of 1 in 4 boxes. Get the point? 2 into 4, 8. 8 megapixel you can make. Yeah, it is totally configurable. Yeah, you can do it. This is proven to be good. Hyperparameter they have already trained, and skip connection is like, so which layer you, which block you're sending the skip connection? One of the hyperparameter. You say where the connection has to be connected. Where is the start point and where is the end point? Skip connection is from here. So after the first convolution, you get a one certain latent features of a low resolution image. You keep that as a reference. Then after that, you train multiple convolution blocks. Sorry. After that, you train multiple convolution blocks, and you keep the, because of the skip connection, you know that how a actual image is looking and what is the convoluted image, whether it is correct or not. You understand, right? Skip connection is more of like, you don't want to.
So do you want to pass through all the data or do you want to copy it from there and then just go past it? It's bypassing.
That is inference time, right?
No, that is skip connection.
Skip connection is okay. So let's say that
Wait, I have skip connection over here. I'll say over there. Okay, discriminator layer is again, which is more of similar to this one, but over here, if you notice over here, the best part about SR is this p-relu. It is similar to leaky relu, where leaky relu is 0.1. Instead of 0.1, you put alpha, it becomes p-relu. Yeah, it is a learnable parameter. Yeah, and in discriminator, you don't use p-relu, you use a leaky relu. That's it.
so just wanted to get the reason we have skip connection with generated networks is because you want to learn the identity from early layers to later.
I'll show you the. I have skip connection. So let's start about p-relu. Don't laugh. Okay. What is the difference between leaky relu and this one is? Leaky relu, you have a fixed slope, 0.01 fixed slope. This is the leaky relu. But instead of this one, p-relu is, instead of 0.01x, you put alpha x. That's it. That is the only difference. Nothing else is there. Fine. Yeah, and yeah, because you have a control over a negative slope also, you have control over positive slope also in p-relu. Okay, this is, I just what is this? It's like how resonance are used completely, how important is and how the evolution is there and all. So super resolution actually started in somewhere in 2006 and with statistics and all. Then after that, using what is this? Some image processing algorithm, basic thing and all. But after that, in 2014, this one Facebook started to think about how to increase the super resolution using GANs and or AI. That's where they started. So first they started with fully connected vanilla this one, fully connected network, not a this one, not a GAN, fully connected network. Then after that they went with the DC GAN, deep convolution network, DCNN, and then finally they came to which one proven to be used is one is this ResNet only. ResNet architecture was giving better results. Then finally, which was that? I forgot. There was some other architecture also after ResNet. Could be something. Okay, then it could be something. That is we are using now. We are using it now. So. No, just for feature extraction.
I'm saying in the context.
That's what. Then yeah, exactly. They use BGG16. Then after that, also they got a good 24 and blah blah. It goes on. So finally, it came to GANs, and they understood that okay, GAN can do way better as compared to other thing. So yeah, this is about the ResNets, skip connection, like ensemble. So this is what he was talking about, f of x, and the output of f of this one is, you have the output of this layer also, and you have what is the previous layer. So you have both. You have the information of how do I say? You have information of first standard also, first standard result and second standard result. Yeah. So because of this, see, generally it happens, right? When we are studying first standard, second standard, third standard, when we reach 10th standard, we'll forget first standard. I don't know rhymes. You know, that is minimal information because you are using it everywhere. But I seriously don't know rhymes. Yeah, exactly. That is why skip connection comes into picture. Skip connection is like you don't want to lose the information. You are upscaling so much. You should have a control of what you are upscaling. What is the information you are losing? What is the information you are gaining? So that's why skip connection helps, and residual network also. Yeah. Okay. Then yeah, this is what I was talking about. ESPSCN, which is before this one, using GANs and all. This is how they used to interpolate high resolution images and all. And yeah. So first is LR, which is bicubic. Computer vision. This one, OpenCV people will know a lot about bicubic and all. Bilinear. It is more of like interpolation way. How it does is, it if let us say what we are doing upscaling 1 to 1 cross 1 to 4 cross 4. Just take one pixel. So you need to fill this 3 boxes. What bicubic it does is, it just puts 0 values everywhere. Then it what is it? It varies the 1 such that that whole pixel value is 1. How to say? It partitions. If let us say one pixel is 1, you have to divide by 4, and you put, instead of 1, you put 0.5, 0.25, 0.25, 0.25, 0.25. So max pool of that is 1. That's how it happens. If you think in an image, you will understand. But what happens over here is, you lose the edge factors. So edge is not like 0 and 1. It is a transition of 0 to 1. 0, 0.1, 0 to 0.2, like that. Pixel values will vary, but that variation is lost. You'll get 0, 1 or 0.51. That's all. That factors only you get. So that is that is bicubic. Next is ESPCN, is more of like pixel shuffle. What it does is yeah, this 3 boxes, it does by shuffling the other pixels. How do I say? There is 1, 1, 1, 1. Okay, and it has to make 1 to 4 matrix, right? This other next pixel of the low resolution will be shuffled to get to generate the. Oh, nice. Okay. Oh, okay, fine. This is normal only. It is not required and all. Everything we will just go. It's not required because outdated. It is no use. This one output is not useful and all. Yeah, sure. We can go for faster than that also. Yeah, network is network is, if you notice over here, there is no this one pooling layer, because we are doing upscaling. We are not doing downscaling, right? So there is no pooling layer, and oh, okay, comes to the loss function basically. So nice question, because I don't know. I didn't write the paper because it is proven, man. It is generally what they do is hit and try only. They would have tried with leaky ReLU, it didn't work at all. First of all, leaky ReLU was not even introduced. They randomly just gave up 0.01 and finally like, okay, fine, this works well. That's how, more of like then some guy would have said like, why it is 0.01, why can it be 0.1, why can't it be a learnable parameter? Then he is like, put it alpha, it became PReLU. Because you maybe, yeah, why would you use a PReLU? Because
the objective of using a ReLU is as an
activation function, that is fine.
And what do you get out of ReLU? What do you get out of using ReLU?
It is fully positive.
Essentially, for certain
not pixel values, weight values. Weight.
For certain weights.
You don't want the weights to go down to less than 0.
Less than 0. I don't want.
Less than 0. Leaky value is you allow the weights to go less than 0 and to 0.01 maximum. Yeah, one is the vanishing rate. This one leaky value was introduced for.
So why do we need that in the generator?
Maybe. I can't give a static answer on this. I can give a static answer on this. Okay. Dropping totally. You want to keep a negative intelligence also. You need to be dark sometime. Cool. Yeah. So regarding the loss functions, loss function, what happens is if you consider bicubic everything, loss function is from low resolution to high resolution is you have a ground truth, you have high resolution image, super resolution image, pixel to pixel check, and check whether this one loss is 0 or not. Pixel to pixel. What is that? Euclidean distance. You can just think Euclidean distance. So loss should be 0 in HR and SR. Correct, right? That is correct. So that is the normal loss which was used previously for DC GANs, not DC GANs. Previously using deep convolution networks and all, not GANs. So, but in case of GANs, you can't use that because one is that when you use pixel to pixel difference, you lose the edge vectors and everything. Or this one model will try to find a way to keep the loss as 0, but information gain as 0 also. You lose the information. I can draw later and show you that. I can. That is it. Okay. This is different. So we in case of GANs we use perpetual loss. Perpetual loss is in this yeah, perceptual. Okay. Thank you. Yeah, in this case the perceptual loss is content loss. It's faded, which is adversary loss also, which will get added. So this is content loss. What we are talking. Content loss is what is the content you are losing, pixel wise. So instead of going pixel difference, you apply a VGG19 or any feature X factor. You get the latent vectors. Do a Euclidean distance or distance check on the feature vectors of high resolution image and a super resolution image. If this feature vectors the distance is 0, there are less values, then it can do the thing.
So you're not actually comparing adversarial generations with ground truth. You're actually comparing related spaces.
Exactly. That is how it is. That is the content loss. Yeah, sure. Yeah.
Can we show the architecture concept? Because I'm trying to make sense of it. Just a different loss function. The network architecture is also different. The loss function is changed. So.
Okay. So it will be here only. The output of this.
So that equation at the top. So instead of G of here GZ, now we have G of
low resolution image. Both is an image.
So there was X and Z.
X and Z is replaced by IHR and IR.
HR and low R.
Correct. Nothing else has changed. Yeah, I'm sending this. Wait, VGG19 is there should be somewhere here then. It should be. This is VGG19. So after this only you get the feature extraction.
After that only we have actually some output.
Frozen. VGG19. It is a pre-trained. You are saying architecture or no? You can train the pre-train also. At 0 it is trained. Then after that this is frozen. Then after that this is trained. That's how pre-training works, right? will be somewhere here. Just think that input image is there, VGG19. I don't know about this architecture. I'm saying about my code. Okay, input image VGG19. You will get this one feature extractor. That feature extractor, and here also again same thing goes in discriminator. Input image VGG19 feature extractor. These two are same. You'll get 256 dimension. I guess I don't know exactly.
At the end of the VGG19, just ask based on this question. At the end of the VGG19, we get an image, and that's where you.
You don't get the image in VGG. Latent space. Vector. Correct. 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 Totally correct. Instead of comparing the images, you compare it.
So, in the equation, so for the distance, for the first part of the equation, what we are looking at.
1 minute. G of ILR is super resolution. This full term.
This entire term is super resolution.
This is low resolution. G of ILR is super resolution, and high resolution is the ground truth. HR is ground truth.
X is replaced with HR, Z is replaced with LR.
Cool. I'll run. What else is there? Yeah. So content losses I said, right? This one feature vector difference and all. So these are the examples and all. So using bicubic, you lose all the information basically. That is like useless. Then after you are using this SR-ResNet, you get some information. And SR-GAN is pretty much, it's like, see, you get the image, it looks good. You get value also of, this was MOS I guess value or MSC value or some value. So value is loss also less. In ResNet should be, there are two. Yes, correct. Similarities, structural similarity in image matrix or something. Yeah, that one metric is there. There are two metrics basically. PSNR and yeah, PSNR and SM. I don't know, some metric. It is PSNR, I guess. It should be. Signal to noise ratio. Peak signal to noise ratio. Correct. Peak signal. Correct. Yeah, SR-GAN is this. This is the original image and SR-GAN image. But the problem was coming out there. This PSNR and SM does not give the actual indication of whether the image contains the does it contains all the content or not. These values doesn't directly specify. So what they did is mean opinion score, which is there. They made the output of the images of a real image and fake image to the actual this one some multiple entities per persons or around 1,000 persons or something, and they do mean opinion score to generate another score. So in that case, mean opinion score was very high as compared to SR-GAN. That's what. Oh, what is going on? It is just minus.
No, these equations. So the first one, ISR is equal to, or LSR is equal to LSR of X plus X to the power minus 3. What is that?
I'll tell you. This is an adversarial loss now. So it is a weighted loss of content loss and adversarial loss. So LSR is nothing but a mean squared error. If you notice over ISR and ILR. G of ILR is SR. HR minus SR feature vectors.
So
it's a. It's not penalizing. It is alpha. It is in. We are not totally depending only on the content loss. We want to know what is adversarial loss also. What is the hyperparameter? I didn't fix it. I didn't fix it. So weightage you're giving. Lower weightage to that. So which one?
For the content loss.
Content loss.
And let's say you have two options. And the first equation.
Yeah, it is VGG loss only. For GANs, it is VGG loss. The feature vector loss. MSC mean squared error. latent space because even that is numbers only, right? If you notice over here also high PSNR, exactly, these are PSNR only. So bicubic has 21.59, SR-GAN is also 21.15, but all the content is lost over here as compared to this. So you can't use that matrix. That's what I was explaining. What is that there?
Image size. Image size.
What is R-squared? What? I don't know. Correct. 4x. This is 4x, so it should be that. R will be that scale, I guess. How much you are scaling up?
Aspect ratio.
No, I think it is RW into RH. That's why it became R-squared. RW is a number of width and height.
Width and height, I understand. What is R?
Oh, image size.
Scaling, right? That's what scale. So in our case, it is upscale. So it will be 4. R should be 4 then. Yeah, it's scaling factor also. Full deep. Oh, yeah. Content loss is the really important, right? See, first of all, generator input for the generator is not random noise. So it already contains an image. So it is not an adversarial image. So there is no not much fake items which is present over there. Eyes are there, upscaled. It upscale, it will still be eyes, but we are not checking whether the eyes is actually eyes. Adversarial loss is that. So, but we don't want to totally throw away the adversarial image. What could the black portion of the eyes is fully covered? That is still the fake thing which is there. No? So that is why you are minimizing the general loss.
Yeah, I want to just add one point here to go back. If you see this carefully, this is y minus y dash square.
Yeah.
Is mean square error.
Mean square error.
Nothing more. This is the real high resolution image minus the generated from low resolution noise. So it is y, the known y, high resolution image minus the what the I generated from the low resolution. It is y minus y dash square divided by total number of samples. So this r square here because this is also square. So there is some r scale.
What is scale? That is scaling factor.
Scaling factor is happening r
Correct, right.
The scaling factor. So this is basically mean square error formula.
Yeah.
In this context, and there are two mean square errors. So one is for the generated image, one is for the original x. So now y minus 10 to the power of minus 3, that's the hyperparameter they found by experimentation. So they are low weighting this loss, they are overweighting this loss.
Yeah.
That's what they are doing. It's a combined multitask loss. Previously also we had plus 2 loss. Right?
Additionally, thing is already width and the height. Scale.
These are scaling factors or normalizing because I am summing that twice. So there are two summation and normalizing. But exactly we have to see exactly what you are writing through the image. Just like you normalize the number of samples.
Additionally, this is a pixel loss. This is not VGG loss. So if you see over there X, there is MSE and VGG loss. He was saying that same thing. Yeah. Cool. So this is the VGG loss. Same thing, which is the feature vector of both is this one changed or difference of the feature vectors has been seen. Cool. Yeah. Sample image. I mean ground truth. No. Which X you're saying? Small X or which X? X is some random variable which is defining whether it is a MSE loss or a pixel loss or a VGG loss. So
this is your real image. This is the generated from low resolution.
Okay. Wait. See, this is not an image. This is an indicator which loss you are choosing. It is an indicator of MSE or VGG. Pixel loss or a VGG
So
loss?
the first loss comes from the upper part, like you had generator on the lower part, and the true label was on the upper part. What goes to the discriminator in the basic.
Correct.
Okay, that first loss, LSR, that comes from which upper part?
That comes here.
Okay, which comes there?
This
The
one.
lower part, generator. Both comes there.
Both is this. There are three losses: content loss, generator loss, discriminator loss.
Content loss is from feature extraction.
Content loss is after the output is being provided or output has been generated.
You'll have to go on the board.
No, see, in the previous slide, he was using the MSC formula. In this slide, he is using the VGG formula.
That's it.
That is the difference between these two slides.
VGG vectors. What is the high resolution pass to VGG? You get VGG vector. Latent vectors. The super resolution pass to VGG. You get super resolution latent vectors. What is the difference of those? That's it.
That difference is first.
VGG loss. This one.
That first one.
This one.
Okay.
General adversarial losses that we get the loss of generator and discriminator. That is this.
So this takes similarity. This was the
Correct.
This takes similarity.
This is for similarity. This is to maintain the content or DPA.
This is the original GAN loss. This is the original GAN loss. In this SR-GAN, we have added a new kind of loss which we call as content loss. The original GAN loss is as it is. That is adversarial loss. In this SR-GAN, we have added a new kind of loss which we are calling content loss. That content loss is being added here, and he has two variations to it. First, he was using MSE formula, and now he is using VGG, which is somewhere intermediate latent feature.
Cool. So we didn't come to this. Next is that. So if you so adversarial loss is the normal loss, what we discussed about the GAN loss. So that is what is here. So perpetual losses, whatever, perceptual loss. So that is the content loss plus adversarial loss. Yeah, this is the architecture of this what we'll be using and all. Yeah, we'll be using a train VGG network, VGG 9. The output of the VGG network of both this, you find out the perceptual loss, and normal generator discriminator, you find the GAN loss. Perceptual loss is the both. Pixel shuffle, which one you think? Pixel shuffle, it's like, how do I say? One, during the upscaling, I said, right, one pixel is one value. 1 cross 1, you're moving to 4 cross 4. One, some value, random value, some 3 random values there. Here, I don't know, this is one of the parameters. What they found is, if you do this one, if this one shuffle the diagonal values, it trains faster.
Okay, so
I don't know why. I don't know why, how and all, but they have found it. If you shuffle the pixels, maybe you get a random value and automatically it gets trained faster. Doesn't get. Sparsity is you put more zeros.
No, you first you pad it by zero.
But
In this case, you are doing by two. Either you pad, so 1 cross 1 can become 4 cross 4 even with zero padding. Okay.
Correct.
Okay. But in this case, you are doing by two.
It is not bicubic. We are not.
You said no, but it's by two.
After the convolution, right? Convolution automatically upscales. Convolution layer will put some random value. After that, you are doing pixel shuffling.
No, but how do you take each one from 4 cross 4? You are doing
Upscaling, up convolution.
how do you do it? How do you do it? You can do zero padding. Okay. One of the ways is zero.
One is zero pad.
transpose convolution. It's transpose convolution. In TensorFlow, there is a transpose count layer also.
There are multiple ways. So it is like, so some is one major factor is zero padding. What you said. There is random padding also. Random. They have found it. It is.
The thing is, this paper is 20 pages. It's a very long paper. There's so many thousands of fine points, so it's very hard to sort of explain all of them.
Okay,
It's
see.
an overview.
I'll explain you this one. Why it is there is, let us say, hair is there, or one line you can consider. The one line you don't know whether the pixel value should be present in left or right. The black line, it can, if you put it in a high resolution image, the line will become distorted. So the positional intelligence loses where the pixel value has to be. It found out that this pixel has to be dark, but you don't know which pixel, which position it has to be there to get that fine line. If you don't do pixel shuffling, you can't find out, you'll get a distorted line. That is why pixel shuffling is used, such that pixel shuffling happens only in that 4x4.
So pixel shuffling is also a vector operation.
That 4x4 or for whatever your scale vector is. Oh god. Okay, this all is okay, control loss 1 and control. Okay, this all is you understood, right? Yeah, rest everything is fine. This all is what is the metrics and what is the loss function, everything. Yeah, so this is what is you can see. So when you're doing a zooming and saying in SR-SNet, you don't get that crystal clarity. After using this SR-GAN, you get full because you'll get the edges and all properly, more an original image. So this looks more interesting.
So you're saying out here, okay, I don't want to bias based on that one. Thanks.
Cool. Yeah, this one also you can see. So because of the SR-ResNet, these parts is totally smudged. Totally smudged over here and all these and all. But
those techniques help
preserve the this one lines and edges, everything like that. Totally, yeah. Yeah, but it is proven that VGG 19 is sufficiently enough for calculating content loss.
So in sum total, you look at that's pretty much basic.
What did I say at the starting? Architecture 90% is same. The 10% change is only creates a very big effect. Yeah. Loss function, you increase one parameter and you're good. That's it. Cool. This is done with the this one presentation and all. You can head for lunch. I'm hungry.
I think we can continue.
Yeah. So if you okay, regarding the code.